Okay, so yeah, welcome to the live session 1 of the NPTEL course Chemical Process Intensification. And my name is Mohammad Hussain, and I'll be taking the live session 1. And I am actually a PhD student in IIT Guwahati in Chemical Engineering branch, second year PhD student. And so, yeah, so let us start with the course, live session 1. So, what is process intensification? Any chemical engineering development that leads to a substantially smaller, cleaner, safer, and more energy efficient technology is called as process intensification. So, many authors have tried to present a different definition of process intensification, adding much more detail to it. But if one has to summarize what is process intensification in one line, it would be to include these 4 characteristics: that any sort of development that will lead to a process that leads to a smaller, cleaner, safer, and more energy efficient process is called as process intensification. So yeah, that is what how we can define process intensification. Now, the process intensification, sometimes it is also, referred to as process improvement, but that is not the case necessarily. I mean, the process improvement is a bigger subset, so, and process intensification comes under it, and sometimes it may differ from it also. So, if I would have to say what is the difference between of those, process improvement looks at a continuous but small but continuous changes to a process, and that to a well established process, whereas process intensification aims to radically radically change a process in a very the time range can differ, but it radically changes the process. For example, you might be conducting one reaction in a big batch reactor, but then under the process intensification you might decide that okay, a micro reactor would be a better thing. So then you significantly scale down your batch reactor to a micro reactor. So that's a radical change. But process improvement is like that, okay, if you, for example, if you have already a well established, let us say, distillation unit, so how can you improve your purity of the product? Let us say, at instance that you might be getting about 96% of purity, how to make it 97, 98%, so that 1 or 2% counts a lot. It is very difficult to increase that, but if you can increase that just 1 or 2%, then you might be having a better yield, and you might be saving a lot of your capital cost. So yeah, so there you might go that okay, that is process improvement, and there you can then optimize for, let us say the market has gone down and the demand has gone down, so according to the market you will optimize or you will improve your process. So that is continuous, but yeah, continuous but smaller, not a radical change. So yeah, process improvement on the other hand is a broader term that encompasses a wide range of activities aimed at making incremental or gradual enhancement to an already existing process. So yeah, that is the definition of process improvement. So yeah, that is that. So while process intensification aims to maximize the output and efficiency of a process by fundamentally altering the process design, equipment, or operation, but on the other hand, the process improvement will just do small incremental changes. So if I have to summarize, I would say that okay, process intensification focuses on transformative changes to the process to achieve significant efficiency gains, while the process improvement involves continuous incremental efforts to optimize specific aspects of the existing process. So yeah, process intensification involves radically changing and trying to develop a new process. So yeah, so that is the definition of process intensification, that okay, any chemical engineering development that leads to a substantially smaller, cleaner, safer and more energy efficient technology is called as process intensification. Now let us go at the brief history of process intensification, that okay, how it came into being. So process intensification actually started a long back in 15th century, 16th century. It has been a long practice, but formally it was initially documented in the late 20th century in the United Kingdom. So its formal documentation started in the United Kingdom, British. So British people did that, and in the late 20th century. And the earliest example of the formally documented process intensification was the high G distillation unit of the Colin Ramshaw, 1983. So yeah, that was one of the formally documented physical working manifestation of process intensification, that high G distillation unit by Colin Ramshaw. So, but even in the late 90s, the process intensification was primarily focused on 4 areas. So, using of centrifugal forces, compact heat transfer, intensive mixing, and combined technologies. So, in the United Kingdom or in the Britain, where it was first formally documented, and in the Britain itself, the people were working a lot on that. So their primary focus was on using centrifugal forces. So basically, if you centrifugal force, you can enhance mixing using centrifugal forces, and compact heat transfer, that okay, how can you do much more radical change in the temperatures or more heat transfer in a smaller and smaller device. So spatial reduction of the heat transfer equipment, and intensive mixing. So as we all know, and it has been a very common saying, that okay, the heart of the chemical engineering lies in the mixing. So how well you can mix two reactants, or how well you can mix two raw products, will define how better they are getting reacted, and they will give better products. So yeah, the heart of the chemical engineering lies that okay, how better you can mix two reactants. If they are two immiscible phases, then yeah, you need to go for different approaches like emulsion, or so yeah, the idea behind that is that okay, how you can basically intensify the mixing. And then the fourth area was that okay, combined technologies. So let us say, so yeah, that intensification in the fourth combined technology came like that okay, how can you combine both the reaction and separation stages. So in those times, even today also, the reaction happens in a different reactor, let us say in a batch reactor or CSTR, continuous stir tank reactor, and then the product with the byproduct goes to the separation unit, where it gets separated. So but intensification can be performed if we can combine both of them together, that okay, the reactor and the separation stages are combined, so that reaction happens and the separation simultaneously happen. Reaction and separation simultaneously happens. So that is the idea behind the combined technologies, that okay, how you can combine two technologies. And for an example, in that late 90s itself, the onion skin methodology for the process intensification was developed to basically develop an integrated equipment, and onion skin methodology to develop an integrated equipment included reaction, separation, heat integration, process control, safety. So the idea was that okay, to make an integrated equipment or an integrated plant itself, you first need to combine from the reaction step, the reaction will happen, then the separation, and once you combine the reaction stage and the separation stage, then you can think of integrating the heat. Let us say the reaction is an exothermic reaction, so you can use that exothermic reaction to basically start the initial reaction step. I mean, you can, to bypass that initial energy barrier, so you use that exothermic reactions heat itself to start the reaction. So yeah, once you have combined the reaction and separation stages, then you can think of integrating the heat transfer. Then once you have done that, then you can think of performing process control, that okay, how can I control my process for a given selectivity or for a given conversion, how to control my process, and for different quality of raw product and different quantity also. So yeah, then you can think of integrating the process control into it. Then after it, then you will think of safety, that okay, how can I operate this integrated plant in the safest manner possible. So yeah, that was the idea of the onion skin methodology for the process intensification, developed in the late 90s. So yeah, so centrifugal, okay. So the vision of process intensification. Now we have first defined what is process intensification. Then we have discussed what is the brief history of the process intensification. Much more, the history has been in detail. Has been discussed in much more detail by the sir, by the Professor S.K. Majumder sirs, whose course is this. So you can go through that. And then after the history, then what is the vision of process intensification? So I mean, while performing the process intensification, so what it gives to it provides to you. So the vision of process intensification is actually quite a subjective topic, and it basically differs from company to company, organization to organization, institute to institute. But the core principles and the objectives can be defined in very simple 6 points. The idea behind the core principles behind the process intensification is that okay, we need to efficiently use the energy and the resource. So the raw products and the energy must be used in an efficient manner. There should be no wastage of it. There should be no the wastage of the raw product or the energy used itself. And then the second principle or the second vision of the process intensification is to reduce the environmental impact of the particular process or the plant. So that yeah, it becomes more cleaner. And then the third idea is compact and modular systems. That okay, process intensification, I mean, the one of the very important vision of the process intensification is that okay, how less spatial area or the less spatial volume you can use to perform a given process. So in a conventional reactor or in a conventional process or a conventional setup, a process might be taking a lot bigger volume, spatial volume, but you can reduce or you can make the process of the plant much more compact and take less spatial area. So, and then the fourth is process safety and control. So how safely can you perform the process? I mean, what are the loose points and the loose nooks where a life can be at a risk? So there might be a particular step in your process, in your plant, that might be highly exothermic and can potentially go into a runaway condition. So what are the safeguards and the control mechanism against that, and how safely can you perform even in those runaway condition? I mean, the reactor, what is the safety protocol regarding that? And then comes the enhanced product quality, that okay, ultimately it is all about that okay, what is the quality of your product, what is the yield of your process, so how much product can you produce in a very less time. So this is also very important. And then comes the interdisciplinary collaboration. So interdisciplinary collaboration gives a, you a different vision or a different perspective regarding operation of your plant. So you might be producing a certain certain species by performing certain chemical reaction, but that same reaction might be happening in the nature in the nature by itself, but in a much more efficient manner. So then you need to basically learn from the nature itself. So like, I mean, if there has been a very quite a good saying that okay, if the chemical engineers would have to design the digestive system, so they would take a lot bigger volume. So we need to learn from the nature itself, and those learning can be potentially coming from a biological discipline. So then you need to collaborate. So interdisciplinary collaboration is a must. And then you might be doing the plant design, so but the mechanical engineers might be performing computational fluid dynamics study or the hydrodynamic study of a particular geometry. So then you can collaborate with the mechanical engineers that okay, how to get that how to optimize your plant geometry for better mixing, so that the reaction can be made, reaction rate can be made faster. So yeah, interdisciplinary collaboration is also a very must. So that is the vision. These are the vision for the process intensification. Efficient utilization of energy and resource, and reduction in the environmental impact, and compacting and modularizing the plant or the process, and the process and ensuring the process safety and control mechanism, and enhancement of the product quality, and improving the interdisciplinary collaboration. So for example, the company DSM, so Dutch State Mines, so it is a company that focuses on the minerals and the food industry. So the company DSM embraces process intensification under their triple P concept: people, planet, and profit. So yeah, so there are various different vision for different companies, different institute, and the company DSM embraces the triple P concept, their triple P concept: people, planet, and profit. So now coming to the principal features of the process intensification. So we have gone through what is process intensification, brief history, and what does the vision of the process intensification, what does it look like, and now coming to the principal features of the process intensification, that okay, how can you identify that, or what are the features of the process intensification, what it can bring to the table. So it has been nicely summarized by the Gabriel Segovia Hernandez and Bonilla Petricolet in 2016, that process intensification features can be summarized in 3 steps, or a triplet: that molecular process, product, and process engineering. So first you start optimizing or intensifying the molecular processes itself, that or the reaction step, that when one species reacts with another, so how can you intensify that, or how can you optimize and perform it better. Then once you perform the reaction better, so keeping in mind that okay, this is my selectivity and this is my conversion rate, so optimizing however much you can with the molecular process itself, and how much temperature you can go, and how much pressure you can give it to it. So with the given circumstances, with the given values to the temperature, pressure value, and the environmental value, whatever in which the reaction is going to happen, and intensifying it for a given process conditions, for the optimal selectivity and the conversion rate. Then once the molecular process have been intensified, have been calculated and done, then comes product. So the molecular process of the reaction will certainly give you some sort of byproducts also, some sort of waste or waste heat or the spare heat. So it might give you a byproduct, it might give you some spare heat. So then how can you separate the byproduct from the product? So basically then comes that, okay, the separation, or how can you extract if you cannot separate? Then you will perform the reactive extraction or some sort of, so you may employ different ways to intensify that, okay, how can you in a better way, much easier, cheaper and greener way and safer way to obtain your product from the yield of the entire molecular process. So that is the idea behind the product. So once you have obtained the product and once you have established that, okay, this is my molecular process and this is how I get my product, then comes process engineering, that, okay, so this was still the laboratory setup or even to the lab scale. Now comes the process engineering, that, okay, how can you make it in a bigger scale? How can you scale it up? So there the scale up issues might come up and various other things, that, okay, even if I scale up, how can I use less and less spatial volume even if I scale it up, even if I scale up the entire process. So there comes the process engineering, that, okay, how can I engineer a very optimal and efficient, cleaner, safer process. So there comes the process engineering. So Gabriel Segovia Hernandez and Bonilla Petricolet, they summarized all of this in a very 3-step triplet. So now in the 2010, a paper by Lutze, they identified the principal features of process intensification. So yeah, this is a very subjective, not very, I would say subjective, but it comes with different perspective. So they were Gabriel Segovia Hernandez and Bonilla Petricolet were able to summarize in 3 steps, but the Lutze gave a much more extensive steps to it, and in his paper, 2010 paper, he identified the 4 different integration or the 4 different steps for the process intensification, 4 different features of the process intensification. So these 4 features by the Lutze's paper in 2010 list that integration of unit operation, integration of functions, integration of phenomena, and targeted enhancement of a phenomenon of a given operation. So Lutze, the integration of unit operations, like, okay, you can combine 2 unit operations. So like I said, reaction and separation, you can combine them, or reaction and extraction, you can combine them to make reactive extraction process, or the membrane reactor, where the reaction will happen and the separation will simultaneously happen. Reaction and separation will simultaneously happen. The membrane reactor are one of the very great examples. Even the micro reactor, where you can combine them. So like lab on a chip, so you can combine 2 different operations on that same microchip itself. So that is the integration of unit operations. Then integration of functions, that, okay, you can integrate different functions. And also the integration of phenomena, like you can integrate the convective and the diffusive mass transfer. So in one case you might be observing there is a diffusive mass transfer. So, and then you can basically include the inertial effects to even combine the convective effects of the hydrodynamics to enhance the mass transfer. So yeah, that combination of the convective and the diffusive mass transfer or the heat transfer can come as integration of phenomena. And the targeted enhancement of a phenomenon of a given operation. So that was the integration of phenomenon that I just discussed. Now, if you want to specifically enhance, let us say, the convective mass transfer, so then you might go for different approach, like, okay, you might employ magnetohydrodynamics, like You may use magnet to manipulate the fluid. If your fluid is, let us say, a ferrofluid or a diamagnetic fluid, or consisting of some sort of ions. Or you might use ultrasound to basically perform the cavitation to generate microbubbles. So you may, to enhance the mass transfer. So microbubbles will give you very high specific area, and that high specific area will lead to an increased mass transfer. So there you can perform the targeted enhancement of a phenomenon. So individually, I would like to discuss that, okay, integration of unit operation. So the reaction and separation unit operation can be integrated by combining reactor and membrane unit. For example, the membrane reactor. So there might be a solid catalyst that might be, so the mesh or the membrane mesh might be doped with some sort of catalyst, and then the reaction may happen on the mesh itself, membrane itself, with the help of the catalyst that has been doped, and that the membrane has been doped with the catalyst. So the reaction will also happen, and side by side, simultaneously, separation will also happen in that same unit. So yeah, that is the integration of unit operation, and the reaction unit integration of the unit operations, reaction and separation unit operations, to give out membrane reactors. Now another great example could be combining a reactor and adsorber unit. So the adsorption, for example, adsorption reactor for sorption enhanced water gas shift reaction. So if you have water gas shift reaction happening, so if you adsorb the byproducts itself, if you adsorb the coagulated particles from the water gas shift reaction, so then you might basically generate a better driving force for the reaction to happen, because the efficiency of the or the conversion rate, or the reaction rate of the water gas shift reaction drops significantly when the concentration is on the product side. So as soon as you remove the product, so byproduct also, by adsorption, you can basically keep your reaction rate very high. So that is the idea behind combining the reactor and adsorber unit to give an adsorption reactor. Another great example is combining a reactor and extractor unit. So like for example, the separation of carboxylic acid from the wastewater via reactive extraction. So yeah. But the second principal feature given by the Lutze et al. In 2010 is the integration of functions. So again, we can combine the conversion and separation into a membrane reactor. So it is not the conversion and separation are not just unit operation; they also come under as functions, different functions what a plant performs. Under what a plant, some functions, two different functions that undergo operation under the same plant. So yeah, you can combine the conversion and the separation processes in the membrane reactor, that which I had just discussed. Sorry. Another thing you might do is combining conversion, contacting and mixing in a static mixer in continuous flow microreactor. So you can combine the conversion, contacting and mixing. So for example, what happens in the continuous flow microreactors is, so let me just first define you what is a continuous flow microreactor is. So microreactors are the reactors that have handling volume in the range of microliters. That's why they are called as microreactor. Or another way to define it is that their characteristic dimension is less than or equal to 1000 microns or 1 mm. So you can see in this picture that this is one microreactor. So there is a scale here present for your reference, that okay, this scale is of 11 centimeters long. So this reactor is of approximately 10 centimeters long. So yeah, from 1 to 11, approximately 10 centimeters. So in the lengthwise, you might be seeing that, okay, there are some U bends present here, U bend, and then there is a straight section. So this reactor is actually of 2 meters length. So the reactor length of this micro reactor is approximately about 2 meters. But yeah, you can see the diameter of this channels of this circular cross section micro reactor channel is 1 millimeter. So the definition of the micro, so this can come under this reactor comes under the definition of micro reactor, and the definition is reactors, continuous flow reactors. So not like batch reactor, or not like your CSTR. CSTR is continuously stirred tank reactor, but there is no continuous flow of it. So a plug flow reactor can come under the continuous flow. So yeah, there is a flow inside CSTR, but it is not continuously going, there is no outlet to it. So you might be mixing with using some flow, but it is not continuously going out. So yeah, the process itself is contained in one conduit. So yeah, continuous flow reactor that have their handling volume in the range of microliters, and their characteristic dimension is less than or equal to 1 mm or 1000 micron can be called as microreactors. So what happens in the continuous flow microreactor is that you enhance the contacting by basically, so for example, if you have a two-phase like reaction, like gas liquid reaction, for example, carbon dioxide is getting absorbed in monoethylamine, so MEA. So the contact between the carbon dioxide bubble and the because gas phase is immiscible to the liquid phase, but the carbon dioxide is getting absorbed from it. So what happens is basically in the micro reactor, the specific area increases very significantly. So the net area available for the mass transfer is significantly enhanced, and similarly for the heat transfer also, because of the increase in the specific area for a given volume, you might get very high contact area, and therefore the heat transfer will also increase, so that you might get very you might be able to control the temperature very efficiently, very easily. And because of the small control volume, you can easily control the reaction, even if a certain reaction is highly exothermic or a highly runaway reaction, coming under runaway reaction. So that can be conducted in microreactor, and the contacting can be controlled easily in microreactor, and mixing can be performed. So these U bend section that you might see, these are introduced to basically enhance mixing. So what happens in the straight channel, straight microreactors is that microreactors have a very big disadvantage, that the flow inside the microreactors is laminar in nature. So basically, if you see the Reynolds number, so the Reynolds number is rho Vd by mu. So the density multiplied with the velocity multiplied by the characteristic dimension divided by the dynamic viscosity. So here the characteristic dimension is quite low, so that makes Reynolds number generally for the microreactor quite low in the laminar range only. So, and you know that laminar range is diffusion limited range, so the mixing is not very efficient in laminar range. So then you need turbulence to basically enhance your mixing. So but what you can do is, by introducing complex flow path, like introducing the U-bend curvature, or making the your channel in a helix manner or helical manner, you can introduce some sort of complex flow structures that may enhance mixing. A great example is, or the idea behind using these U bends are that, okay, you are exploiting the complex flow phenomena known as Dean flow, where the Dean vortices are generated at the U bend. So they significantly enhance the mixing. So the contact is happening by the significant increment in the specific area, or the net available area for the heat and mass transfer, and the mixing happens due to the curved flow path, and then the conversion automatically increases in the microreactors. So yeah, So that is one of the integration of the function, that you combine conversion, contacting and mixing, all three in continuous flow microreactor. And similar can be done for the static mixers also. So the third principal feature given by the Lutz in the 2010, Lutz et al. 2010, is integration of phenomena. So different phenomena can be also integrated. For example, like reaction phase change phenomena and diffusion in membrane and phase change can be integrated into one. So all of these phenomena, that the reaction is also happening and the phase change is also happening. So you can combine both of them, integrate both of them. So another great example is reactive, convective, diffusive heat and mass transfer, volume flow transfer in a static mixer reactor. Just a minute. Hello. हेलो हेलो हाँ, आप कहाँ पर हैं? केमिकल ब्रांच के ग्राउंड फ्लोर में आता है. हेलो, कहाँ पर है आप? So yeah, just 5 minutes and I will come back. मैं रिकॉर्ड कर रहा था, उसीलिए मैं बोला कि आज आप मत आओ. रिकॉर्ड हो रहा है, आप खड़े हो. So yeah, another feature can be that integration of phenomena can happen. It has been given by the Lutz 2010. So yeah, The reaction phase change phenomena can also be integrated. So yeah, that we have discussed. Now another thing is that okay, reactive, convective and diffusive heat and mass transfer can also be combined. For example, the volume flow transfer in static mixer reactor, or the microreactor, what I have just discussed, that okay, you can combine the convective and diffusive heat and mass transfer. So the laminar regime is diffusion limited, but you can basically combine the inertial effects into it to basically enhance the convective heat and mass transfer also. So that is the idea behind that. And the convective heat transfer phenomena in spinning disk reactor, that is also one great example of the integration of phenomenon. So the fourth principal feature that the Lutz 2010 has given is targeted enhancement of the phenomenon of a given operation. So for example, like reaction in membrane reactor. So yeah, that the membrane, so the basically you can enhance by doping the membrane with the certain catalyst, so that can basically enhance your reaction happening in the membrane reactor. So the separation, you can control that, but the enhancement of that reaction can be happen by basically if you choose different catalyst. So yeah, or basically if you dope your membrane with it. And another thing is convective and diffusive heat and mass transfer in the static mixer reactor, that also comes under the integration of phenomenon, but you can also target that. So integration of phenomenon was that okay, you combine two phenomenon, but yeah, you can target the enhancement and the enhanced targeted the enhancement of particular phenomenon that you target. And another was that okay, convective heat transfer phenomenon in spinning disk reactor. So in the spinning disk reactor, what happens is you use basically the centrifugal forces to, you know, that okay, artificial gravity, like the high G distillation plant by the Ramshaw. So why it is called as high G is basically the G's are the multipliers to the gravitational force, like 1G and 2G, what the pilots experience. So that is what they termed it as high G distillation plant. So in the spinning disk reactor, that is also that same, that okay, you use the centrifugal force to basically provide very high forces, and then they basically say it as that okay, high G forces, and then there you can perform the high convective heat transfer phenomena or enhance that. And then comes the diffusive mass and energy transport phenomenon in microreactor. That yeah, again what I have discussed, that okay, in the microreactor you can enhance basically the diffusive mass and energy transport phenomena by increasing your specific area. So one thing was that okay, you can combine the convective convection to the diffusion by basically enhancing by a combination of the inertial effects also. And another thing here is you can target the enhancement of the diffusion phenomenon by basically increasing the specific or the net available area for the mass transfer and the heat or the heat transfer. So yeah, that is the targeted enhancement, or you can combine the two phenomena together. So yeah, that is the basic gist behind the four principal features that the Lutz et al. Has given in the 2010. So now if you see that the basic features, so these were the principal features that the Lutz have given. Now the idea, if you might have caught on with the common pattern, is that they all use some sort of different unconventional fields to enhance some sort of phenomenon. Like in the high G distillation tower, they use the centrifugal field to basically enhance, or even in the microreactor to basically enhance the passive mixing, they use the centrifugal field of the curved microchannel, so to enhance or to perform the process intensification. Or you can also use the ultrasonic field. So I will just come into it, that okay, how you can use the ultrasonic field to perform cavitation to generate micro bubbles. So that is another idea. And another thing is that you can use electric fields to basically generate radicals, that chemical radicals, that species radicals that can enhance your reaction steps. So there you can use the electric fields, or you can use the electromagnetic fields to basically target uniform target and perform a uniform heating in a targeted area. So, and also you can use the electromagnetic field. So the electromagnetic fields in the longer wavelength range is microwaves, and when you go a little bit shorter into it, after the infrared region, you might get the light, the visible range. So you can also use the visible range of the electromagnetic field or the general light to perform the photoinitiation or photochemical reactions. So there you can basically target your light, and these days you can also use the lasers. So yeah, the lasers will give you a very coherent light source. So yeah, I will just go through them one by one. So the process intensification by the centrifugal fields provide the radial shear, and so the idea behind that is that there will be a transverse pressure gradient generated whenever the flow path is curved. So what I was discussing in the microchannel U bend or in the helical, wherever there is some sort of curvature. So the curvature, what the basic idea behind that is you exploit the Dean vortex, so the Dean flow. So how does it happen is basically whenever there is a curvature, so the fluid elements will experience different pressure based on their location on the different radial length. So the outer fluid will experience a higher pressure than the inner fluid. So what will happen is the transfer of the fluid element starts to happen. So basically that wherever there is a pressure gradient, you might see a flow. So the vortex, as you can see in this image, there are two vortices forming, one in the upper section, one in the lower section. So the fluid elements will start to flow like this. So this is what is called as the Dean flow, and these are the two Dean vortices. So yeah, that is the one of the ideas or one of the application of the centrifugal field in the micro channel. And another is that same high G distillation plant by the Colin Ramshaw, that you can use centrifugal fields to basically generate artificial gravity, or that high G's go to the high G forces, and to perform better distillation. So yeah, so the centrifugal fields provide radial shear, and they also provide secondary flow. This secondary flow is what I am talking about, the Dean flow, Dean vortices, and basically enhance the mass transfer and stability and control. So yeah, you can, by changing the radius or by changing the angular velocity, you can control the centrifugal force. So you can perform you can easily control the entire process. And yeah, so this allows you to basically control the residence time also. Now coming to the ultrasonic fields, so the idea behind using ultrasonic waves or the ultrasonic field is to basically generate very short distance pressure gradient. So what will happen is whenever there is a very significant pressure gradient between two short distance, two points that are lying in a very short path, that are having very short distance between them, what will happen is spontaneous cavitation will happen. So cavitation, if you know in the fluid mechanics, what happens is the fluid spontaneously boils. Wherever there is a very low pressure, what happens is fluid vaporizes, and there you generate some micro bubbles, and then when those micro bubbles burst, they basically destroy your equipment, they corrode, so there you can see on your fins that those bubbles, when they strike to that surface and when they burst, so they slowly damage the equipment. So but there it is undesirable, but here what you can do is it might become desirable in your case, that in our case, that micro bubbles, because they are very small in size, and the smaller size, you will get a very high net surface area available for the heat and mass transfer. So yeah, the idea behind that is that you will spontaneously generate micro bubbles using the ultrasonic field to enhance the mass transfer. So yeah, the ultrasonic waves when propagated through a liquid medium generate microbubble, and the waves generate intense mixing condition and enhance transport rates. So this leads to the creation of the greater surface area for the mass transfer. So another thing what ultrasonic field can do is that it can also fracture the processing medium into a reactive intermediate such as the free radicals. And when those free radicals, when you get, so these free radicals are highly reactive. They are basically looking to combine with the other species to perform the reaction. So you can fracture the processing medium using the ultrasonic field that can give you the reactive intermediates such as the free radicals to perform the reaction. So now coming to the electric fields that provide the process intensification, that how you can use the electric field is one of the great example is that you can charge the liquid droplet via polarization and reorient the molecular dipoles by electric field. So first you induce some sort of charge and polarize the liquid droplet. Then you reorient it according to your needs. Let us say if you have a Janus particle. So here I am talking about solid particle. But same thing can be applied to the liquid droplet also, that you can manipulate the liquid droplet using the electric field. So yeah, that is a very interesting domain of magnetohydrodynamics, electromagnetohydrodynamics, that okay, how you can use the electric field to manipulate the liquid droplet. Or basically, if you want to generate a very stable emulsions also, so how will you do that? So the emulsions are basically like your milk. So there are protein globules that are in the water. So the water is actually the main solvent, and the protein globules are present in the water. So so how to generate that stable emulsion is by you can polarize those proteins, and then because of that polarization, they can basically form some sort of micelle structures, and then they can they can be present in the emulsion state for a very long period of time. So that can be controlled if you use electrically charged droplet. So the aggregation, coalescence and settling under gravity can be controlled. So and another thing is, so yeah, it can be applied to enhance. So electric fields can also be applied to enhance the overall rate of the reaction in immiscible liquid system, whereby a higher degree of the stable emulsification is achieved. So yeah, again that was what I was talking, that okay, protein globules and the water are basically immiscible liquid systems. So so how to basically make a stable emulsion is basically you can enhance the overall reaction rate if you are able to make a stable emulsion. So if both the phases separate, then you might not get a very good mixing and your reaction rate will get hampered. So a way is to make a stable emulsion, and the stable emulsion can be achieved by basically if you apply electric field to perform the process intensification in that. So yeah. You can also you can also use electromagnetic field or the microwaves to provide process intensification to a particular process, or intensify the process using electromagnetic field. So the idea behind that is the more rapid control and uniform heating rates afforded by the microwave results in a higher rate of reaction. And under the microwave, ionic conduction comes into play for the heating of materials depending upon the chemical species involved. And the coupled microwave, and you can also couple the microwave and the ultrasound irradiation capabilities to basically enhance the chemical and biochemical processes. So the idea behind that is microwaves provide a uniform heating. So if you would see the papers that, for example, that make carbon quantum dots using the microwave heating microwave method. So, or in any general paper, wherever there is a microwave involved, they always mention the wattage of the microwave. They never tell that okay, at what temperature the particular process or the species was heated. So because the microwave provide uniform heating and they perform in ranges of power. So that is one of the advantages of the microwave, that okay, you can perform uniform heating. So like in the CSTR, or if you are heating, so using a heater rod or something else, so there you might see some sort of dead zones, or where some zones where the heating is not happening and the reactants are there and the reaction is not happening. But in case of microwave, you irradiate the entire field, you irradiate the entire process with the microwave, and you will get uniform heating, and that is very controlled, in a very controlled manner. So you can control the microwaves in, they provide they have very less reaction time, so you can easily do the process control with it. So if you have given a particular set point of a set temperature set point, and you are heating with a rod, so there might be some there might occur some sort of hysteresis to the rod's surface, and so the heating that or the value that you might be getting might not be uniform, might not be easily controlled. You cannot control that, but with the microwaves you can easily control such temperature changes and the heating rates. So yeah, the microwave is a very, you can use that to intensify your process. And also with the microwave, ionic conduction comes into play. So if the species can separate into ions or chemical radical species, then that comes of the ionic conduction. So the microwave can ionize, so these are waves, and they can so basically the ions will get conducted. So until now you might have heard about the general convection and diffusion. Convection due to the inertial effects, and the diffusion due to the concentration difference of the species at two different spatial location. But the ionic conduction is when the ions basically conduct, ions diffuse. So microwave can do that. So, and you can couple the microwave and the ultrasound. So both are, ultrasound uses the physical disturbance on the field, and the microwave is the electromagnetic disturbance. So you can combine these two to further intensify your process. Okay, so like the ultrasound can generate you the microbubbles, and to provide the heating you can use the microwaves. So yeah, you can combine to do even more. You can even intensify more the process. Now the electromagnetic fields provide process intensification. You can also use the visible range of the electromagnetic field to perform process intensification. Like you can also use, for example, like photo initiation as an alternative to the thermal activation of reactions. Inherently clean process requiring only the reacting molecules in order for the reaction to be activated. Light waves, particularly in form of lasers, can provide process intensification in various fields due to the unique properties, precision, ability to interact with the materials in specific ways. So what happens is, so the light waves, so in these days the lasers are available, right? So it is not that you are just doing the reaction in an incandescent light. So light waves, particularly in the form of lasers, can provide process intensification in various fields. So they provide such sort of such sort of process intensification, especially known as the laser process intensification, laser assisted processing. So some ideas that they use the laser is to do the process intensification is like, okay, laser surface treatment. So the laser beams can modify the surface properties of the material by inducing controlled heating, melting, or alloying. So this can improve the surface hardness, wear resistance, corrosion resistance of the components. So there you can intensify your reactor walls or basically change their properties using the laser. So another example is that, okay, laser assisted chemical reactions. So in some chemical processes, lasers can be used to initiate or accelerate reactions, leading to higher yields and reduced reaction times. Laser assisted chemical synthesis can offer cleaner and more energy efficient alternatives to traditional methods. Yeah. Another is laser assisted biomedical applications. So what happens is, in medicine or in biologies, lasers are generally used for various applications, but they can also provide much precise treatment or precise delivery or precise photochemical stimulus to the cells to perform the reaction or to the metabolic processes. So the key advantage here is that, okay, laser process intensification can include very high precision and minimal material waste, reduced energy consumption, and the ability to work with wide range of materials. So yeah, that is the idea behind that. Now the well-defined structures provide process intensification. Now again, that same thing, that, okay, you can use the well-defined structures to perform intensification of process. For example, you can enhance the surface configuration, like I was just saying, that, okay, you can use lasers to basically make surface area of different properties, of different wettability, or of different surface roughness. So you can enhance the surface configuration using by using well-defined structures. And another thing is that, okay, you can use molecular scale structures. So there are various papers where they have made molecular cylinders. So like where the reaction is happening when or the substrate is looking very quite smooth, but when you look with a confocal microscope with objective lenses, you might see that, okay, there are small cylindrical structures, and the catalysts are loaded on them, or the cylindrical structures are doped with such catalyst. So they basically mimic what we have in a natural in our intestine as alveoli, not alveoli, but those finger-like structures. So basically they enhance the surface area, net available surface area for the reaction or for the adsorption to occur. So yeah, that molecular scale structures are in a this is a very hot topic for research as of now. So that, and those can be used to to make molecular reactors that in the scale of molecules. So you use different molecular scale structures to make molecular reactors. Another thing is meso and macro scale structures like channel reactors. So like you can use the lithographic technique to basically make different types of micro reactors, channel micro reactors, micro channel reactors. So lithographic process is that they used to make the PCB chips and the printed circuit board chips in the Intel, what is in your laptop, in your graphic cards, etc. So you can use the lithographic technique to etch into the materials and make micro channel reactors of different configurations. So like you can make a straight micro channel, but then it is a straight micro channel. So if you want to induce mixing through DIN vortices, so you might introduce one single U bend, or if you want to introduce more, so you will introduce multiple U bends and make the serpentine configuration of the channel, a micro channel reactor. Or if you want to enhance much further, so you will not stick to just 2D curvature. So a single U bend is of 2D curvature, right? So it is on a single plane. That curvature is just that C type of curvature, or U type of curvature is just on a single plane. So what you can do, you can make the reactor structure, microchannel reactor structure in form of helical, like a spring structure. So there your curvature goes from just being a 2-dimensional curvature to becoming a 3-dimensional curvature. So you can make helix like that. Now what if you rotate that spring structure over a ring or over a circular path? So there you might get a helical structure of much more complex flow path. So those are like meso scale structures of different micro channel reactor or milli channel reactor. And in the macro scales, you might implement different sort of baffles, that or like you can use different structures, like in the CSTR. What generally they use is some sort of general turbines or the fins for performing the mixing or the continuous stirring. So there you can use general stirrer, or you can use different turbine known as Rushton turbine. Or if you are into research, you can also develop a new type of turbine that can perform a better mixing. So there are a lot of works on it. So that comes under the macro scale structures, so that you can change the turbine structure to perform basically better stirring of and the better mixing in the CSTR. So another is large interfacial area for efficient contact between reacting streams. So, or you can use very large areas for the so that large interfacial area to perform an efficient contact can be achieved again in micro reactors itself. So it is not generally limited to the micro and nano scale, but can be let us say if you are performing in the CSTR, then you operate that CSTR in bubbly flow regime, so that the bubbles can go into as small size as possible, or you basically try to perform so yeah, the goal is that the smaller the bubble, the higher the the net available interfacial area for a given volume, to perform the efficient contact, to perform the mass transfer, and eventually the reaction between one of the two phases. So yeah, so that is the goal behind that well-defined structures can do that. So how will you generate those micro bubbles? So there you will use a different sort of aerators, or different structure of aerators where they can generate very small micro bubbles. So that is the goal behind that, using the well-defined structures to perform process intensification. So these were the few examples, few basic features. So the Lutze et al. 2010 gave the that okay, four basic steps of four principal features: integration of unit operation, integration of functions, integration of phenomena, and targeted enhancement of a phenomenon of a given operation. So yeah, these four were the principal features. Then we have discussed we have discussed in detail about the four principal features by the Lutze 2010, and then we went on and discussed about that, okay, what are the basic features. So these were the principal features. Then what are the principal features that can provide process intensification. So there we discussed some basic features that are available that you can use to perform process intensification, like centrifugal field, ultrasonic field, electric field, and electromagnetic field in the microwave range, and then electromagnetic field in the visible light range. And then we used how you can also use the well-defined structures to perform process intensification. Okay, so yeah, then let us discuss, okay, when it comes to the strategies for process intensification, what are the strategies that are available for the process intensification? So the strategies that are available for the process intensification can be divided into basically three different so there are various way to basically define the various way to give strategy for process intensification, but broadly they can be classified into three domains, or three, not domains, but three steps or three classes. So the business, in the side of the business, what looks like for the process intensification is plant miniaturization. That okay, how small or how can you miniaturize your plant? So basically, so that you are not utilizing some sort of, some area is not wasted, some volume. So the reduction in the spatial volume where the plant resides. So that is the idea. So if you occupy less size, less spatial volume, you need to basically pay less rent, or for the pay less for the smaller area. So that is the area of the land that you are going to purchase. So that is the idea, that okay, in terms of business, how can you miniaturize your plant miniaturization. and so that you use optimally what is the area and the volume available to you. And then comes the capital cost reduction, that okay, how can you reduce the capital involved in the business. So how can you reduce, or how cheaply you can obtain the raw material, not of bad quality, otherwise your process will get compromised and your quality and your product will get compromised. So while maintaining the quality of the raw product, how can you reduce the capital cost? Like you can reduce the cost of the logistics involved by reducing the distance between the raw material site where it is where it is getting refined or where it is getting obtained, and the distance between that mine or that site where the raw material is obtained and where it is getting processed. So you can reduce the logistic cost by reducing the length or the distance between them. So that is how you reduce, that is one of the way you reduce the capital cost involved. Or you can, yeah, again, plant miniaturization. So basically the smaller size you use, the less capital you invest in the procurement of land. So in the business side, that looks like that. And wise distribution of units and hubs. So you might have a separation unit in different place and your reaction unit in a different place. So that is not, I mean, if the distance is quite long between two of them, then you might again need to pay for logistics, or then you might need to transfer your products and the byproducts or the yield to the processing or the separation unit. So yeah, the distribution should be wise, that okay, you place side by side simultaneously, or even combine if you really want to do that. The distribution, the wise distribution is the idea, that okay, you wisely distribute the hubs and units, that okay, what is required where and what process comes next, and accordingly you place them side by side subsequently, that okay, so that you do not need to go somewhere else, or basically you don't use, I mean, the area in a very inefficient manner. So the wise distribution of units and hubs come into place again. And so the next strategy for the business is that okay, faster introduction of new products into the market. So here comes the advertisement, and basically showcasing your products, and basically how fast can you introduce your products into the market, so the market gets familiarized, and the market chooses your product. So there comes that okay, how, I mean, and if the demand is very high, how can I fulfill that demand? So you need to think accordingly, that okay, how much hubs and the units I need to meet this new demand, and how much my raw product procurement should go, so that I fulfill the product demand in the market. So yeah, that is the idea. And again, so that was some basic strategies for the business side. Now for the process side, so the strategy should be that okay, how can you obtain higher selectivity for your product, for your desirable product, and you discard, or basically how can you reduce the conversion to the byproduct side, or how can you produce less the byproducts. So that is the idea. And higher reaction rates, that okay, how fast can you produce your product, or how fast is your reaction, how can you make your reaction go faster. So that is the idea behind that. Okay, so how can you make your reaction rate fast? So how can you basically increase or intensify the mixing, so that the reaction rates go higher? Or how can you increase the heat and mass transfer in that, so that the reaction rate go much higher? So efficient contact then comes into play. So So yeah. So yeah, so where were we? Okay, so the another strategy in the process side is to improve product purity. So after distillation and after everything, that okay, you get a product that is only 80% pure or 85% pure. So then how can you increase your product purity to up to, let us say, 90%, 95%, or 99%? So that every 5%, 2%, 1% matters a lot. So people pay good bucks for good quality product, good purity product. So if your product is able to just perform with an 80% or 85% purity, so it is not good. So people want pure product, right? So they do not want that okay, their product is mixed with something else, that okay, their ghee or oil is mixed with some dalda, or their gold is mixed with some sort of bentex things. So they they give good money for the purity. So the purer your product, the better it will sell in the market. So obviously the price will be very high, and it will be, yeah, so people will then try to go for your product. So that is one of the strategies, that okay, how can you improve your product purity. Another is improving process safety. So improving process safety is a very essential. So because I mean, your reaction, if it is an exothermic reaction or is a runaway reaction, can go, if there is a small nook or some small just disturbances there, the reaction can quickly go into the runaway condition. So if such sort of reactions you are using, if one particular plant is using, then it is highly dangerous, not just for the single operational person there. It might affect the whole plant itself or whole city itself. I mean, if you there is a the very unfortunate example is the Bhopal gas tragedy. So, or your this Chernobyl incident. So improving process safety is very important. So it is not just about single life or about 10 person life or about 1,000 life. So the safety is safety. So so it should be taken up to the highest level. So the care should be taken to the very highest degree to improve the process safety. If you are using such sort of highly exothermic and runaway reaction. So even if you are not using such reaction, you need to basically maintain the safety, that okay, if there is some sort of a mechanical cutter or some sort of a very sharp equipment, that bulky equipment going on, so you need to establish safety protocols, that okay, nobody goes in their operational range. So yeah, that is the idea, that okay, you need to improve that in the process side. And there are various guards that blade guards and all, to basically protect the operational team. And then comes in the process side is the wider processing conditions. So your process is not very very workable process, I would say, or a very good process, unless it is able to work with very wide processing condition. So you might design a process that may work only for a given value of concentration of a certain species in the raw material. So if that is how you design the process, then it is you may not get such concentration value in the raw material every time, right? So you need to basically design the plant such that it is able to perform in the wider processing condition. Even if the reaction, even if the concentration fluctuates to a certain degree, to let us say there is a plus or minus 5% or 10% difference in the concentration of the raw material, concentration of the species in the raw material, desired species in the raw material. So still till then also your reactor must be able to perform, your reactor design should be able to perform. So wider processing condition is always appreciated. So yeah, of course your product may get hampered, but it should not be the case that your processing, your whole process should get stopped. So yeah, we know that okay, if you put garbage in, you will get garbage out. So but yeah, is your process able to withstand that garbage? I mean, it should not get, it should not get broken down, or it should not break down. The entire process or the entire plant should not break down if there is just a one small stone in the reactor. Yeah, although some processing, some plants are very critical about it. So there you need to ensure that okay, how clean is my raw material is. But yeah, wider processing condition is always appreciated, that okay, what are you working with? I mean, how much fluctuations are you able to handle, how much disturbances are you able to handle, how much noise you, so that was just in terms of concentration, how much noise or how much vibration or how much oscillation can your process handle. So if a particular process is very critical, optomechanical critical, so what will happen is then you need to make your process in a very secured chamber, that there should be no vibration going inside it. Or if your process is very there should be no vibration, or there should be no stray light coming into place. So then you need to invest in a very confined clean conditions. So there again, you need to maintain a clean room or some different arrangement, so that may again come into cost. So yeah, so if you have a process that can work with a wider process condition, it is always appreciated. So that makes life a bit easier. So then comes the process integration, that okay, how can you integrate processes? So this is actually what we have discussed quite extensively, that okay, how can you combine two different processes into one. So that is the idea behind the process integration. So yeah, that is one of the big things, that okay, how can you combine the reaction and the separation stages, reaction and extraction stages into one, or reaction and distillation stages into one, so that you make a reactive extractor, reactive adsorber, reactive distillation plant. So that is the idea, integrating processes. And then comes the environmental side of this, the environmental strategy, that okay, you need to also ensure that the energy and the waste reduction, so ensure that the energy and the waste, energy used and the waste produced must be reduced. So that is the idea. Okay, so yeah, that makes a good quote. Energy produced and the energy used and the waste produced should be reduced. Okay, so yeah, so the idea behind that is that okay, you are using the energy efficiently and you are not letting it go away. So if you have an exothermic reaction, So if you have an, so where were we? Yeah. So if your process consists of a highly exothermic reaction, so you can use that stray heat generated into a better use. That okay, to a better use, like you can use that heat generated from an exothermic reaction to basically heat up your initial raw material, to basically go past that energy barrier to perform the reaction itself. So yeah, that is the idea, that okay, you can use the energy, you should not you should reduce the energy, or basically use it in a very efficient manner, and the waste produced or the byproduct, so even that byproduct can also be used, like okay, if you are for example in the soap industry, the glycerol that is produced in the side by side, that glycerol can be used into some different in making of some beauty products or some face masks. So there you can use that byproduct also, so thereby you reduce the waste. So the byproduct is not technically byproduct itself is not a waste until you are not able to use it, until you are not just throwing it away. So if you can use that byproduct itself, so there you reduce the waste. So that is another strategy, that okay, how you can efficiently use the energy and how you can perform the waste reduction by basically putting the byproducts into a good use. And another is less pollution. So yeah, if you generate less waste, if you are able to use your byproducts, and if you generate less waste, you are throwing less waste into the river, or into the, you are discharging the effluents into the air, so you basically do less pollution. So that means that the byproducts itself are getting utilized in some sort, some manner, so it is not getting thrown away, or getting mixed with the nature. So yeah, then it also pollutes less. So that is the strategy in the environmental side, environmental strategy for the process intensification. Now, what are the general questions to be asked for process intensification? I mean, so process intensification is a very wide area and is a very hot topic for research. So, I mean, where do you start? Where do you generally start? I mean, when you have a lot of options, when there is a wide area, you basically ask the question that okay, leave everything aside. Where do I start? What is the initial point? So there is no single hard and fast rule with the process intensification. It is not this, that okay, this is the line and you must march on this line only. So yeah, but you can start by asking the right questions, that okay, how can I decrease my production cost, or how can I decrease my equipment size, or how can I decrease my energy consumption, or how can I decrease my waste generation, or how can I improve my remote control. So how can I basically how much of the plant I can operate remotely, and how much I can improve the information fluxes and process flexibility. So these are some of the questions. These are the right questions that if somebody asks, they might get that okay, this is what I need to focus on to perform process intensification over my plant or over my process. That okay, where is the most costliest part of the process? Is it logistics, or is it a particular, I mean, if I'm getting a lower quality product, how can I basically how can I use my or how can I efficiently use my raw material so that I decrease my production cost, or how can I miniaturize my plant so that my equipment size becomes smaller and smaller. and how can I decrease my energy consumption again so that I save my capital money, and how can I decrease my waste generation so that I can enhance my monetary fund by basically using the byproducts also, and how can I basically nothing should go to waste, because waste means there is no monetary gain in that, and then again that waste is basically nobody wants it, so that becomes a waste, and if you don't want it, the nature will definitely does not want it, and then it becomes pollution. So it is then not just your problem, but then it becomes a bigger problem. And so improving remote control, that okay, if a particular process is highly exothermic or is a runaway, involves a runaway reaction that may go into runaway condition, so how can you remotely operate that condition so that the operating personnel does not get into the harm, so that the safety is ensured. And so yeah, that is the remote control of it, so that there should be no humans going into that, because again, if you plan to basically monitor or control a certain reaction, a certain process manually, so then you need to employ or provide some spatial volume to operate for the operating team to operate. So if you can remotely control the plant itself, you basically save the space, so that you do not need to go inside and do the things. So you can remotely control the things. You do not need to go every night and day to basically change the pressure and all. There is a certain valve on the 7th story, 11th story of the particular process, where a personnel takes half an hour to climb, and then he turns the valve 2-3 times. So if you can remotely control that, it saves a lot of time, it saves the effort also, and yeah, it also saves a lot of spatial volume. So yeah, improving information fluxes and process flexibility. So this again comes that okay, how much process is flexible with it, and how much information is coming. So basically more information is always better, but yeah, it should not be a garbage information. So yeah, but should be a priority information. And yeah, the fluxes, I mean, the better the reporting, I mean, if it is getting reported in terms of seconds, then it is much better, and so that you can monitor the plant even better, so that information, how much information and in what rate you are getting, so that is also very important for the process intensification, that okay, you are getting the information of a particular process in seconds, but not in minutes or in hours or in days, that okay, you check the plant or a particular process on a daily basis. So it is like you are getting you are checking, or you are taking the information on a per day basis. So if you miss one day, it's like okay, the information is gone, the whole day information is gone. So it should not happen like that. So the fluxes or the information rate should be improved. So and these are some of the questions that you ask to perform process intensification. Now, one of the very important strategy for the process intensification is green chemistry. So if you try to intensify the process, a particular process with green chemistry in mind, then it is the most efficient strategy, most important and most best strategy for the process intensification of any chemical engineering plant. So green chemistry is one of the most important strategical movement for the process intensification in the chemical industry, and it is defined as the utilization of the principles that reduces or eliminates the use or generation of hazardous substances in the design, manufacture and application of chemical products. So that is green chemistry. So it is one of the so you can see that okay, utilization of set of principles that reduces or eliminates the use or generation of hazardous substances in the design, manufacture and application of chemical products. So yeah, automatically this fits very well in the vision of process intensification. Now the process intensification can again, so there are multiple classifications of it. Another way to classify the strategies in a very broad sense is there are two ways that you can classify those strategies for process intensification. One is equipment development strategy and another is techniques development strategy. So the equipment development strategy involves that, okay, you improve or you develop your equipment, or you develop some sort of novel reactors. That is one thing. Or you can improve an existing process or the existing reactor like CSTR. You can change the shape and size of the stirrer to optimally mix a certain viscous liquid. So for a given liquid system or gas liquid system. So this is basically the example, the idea behind the equipment development. So these equipment development strategies involve development of novel reactors, for example like chemical looping combustion CLC reactors, or using developing like fission reactors or ultrasonic reactor, etc. And using of intensive mixing devices. So you change your standard mixers into a better intensive mixing devices, like you can use corrugated static mixers, or for if it is a very highly viscous or highly thick consistency thing, so you can use the modern developed dough and confectionery mixers, etc. So that is if you replace the standard the conventional mixing devices with the intensive mixing devices suited to your systems. And heat transfer devices. So general using the conventional, instead of using the conventional shell and tube heat exchangers, you can use fin tube heat exchangers. So or you can use scraped surface heat exchangers. So basically you will get a rougher surface or better more net available surface area for the heat transfer. Or again, you can use micro heat exchangers in the smaller size so that you can get better heat transfer. Or you can use if you have a standard contactors or standard absorbers, so you can, instead of using that for the mass transfer, you can replace them with a cavitation reactor, monolithic reactor or spinning disk reactor, etc., where you might intensify the mass transfer by using the cavitation phenomena of generating micro bubbles to perform mass transfer. Or you can use monolithic reactor to basically contact better to have a better contact with the solid and liquid substrates. And or you can use the centrifugal force in the spinning disk reactor to perform the enhancement of mass transfer. So we discussed the equipment development strategy. So another is technique development strategy. So another is techniques development strategy. So here you basically improve or you utilize a new or a hybrid separation techniques to perform separation instead of the standard separation techniques. So or you can basically integrate the reaction and separation and heat exchange or phase transition together itself. So this is one example. And or basically you can think of how to think of methods to develop interfacial phenomena, that okay, or to enhance the interfacial phenomena, that okay, using of micro reactors, or so that you can enhance the net available surface area. So that is one technique. Or techniques using alternative energy sources like using light or ultrasound. So or you can use new process control methods. So that is the idea behind that. Okay. So the process intensification is ultimately achieved through adding and enhancing a phenomenon within a function or operation for improved equipment design in order to maximize the driving force or to overcome limitations that occur in the corresponding conventional processes. So the process intensification can be achieved by if you add or enhance a particular phenomena that is occurring within a function. Or what you can do is enhance the operation for the improved equipment design in order to maximize the driving force or to overcome the limitations that occur in the corresponding conventional processes. So this is the idea behind the process intensification. So domain-based process intensification technology in chemical engineering. Now, in chemical engineering, so there are different domains. So in all of these domains, the process intensification is very hot topic. So, but the process intensification is divided into domain-based. So it is quite a very broad area. Now, if you want to start at somewhere, so it might happen that you might be interested on a particular domain. That okay, I want to intensify the process of crystallization, let us say, or I want to intensify the process of absorption. So these are the different domains that are available generally. So these are not all the domains, but these are the most hot topics, or the very hot currently, that are domain-based process intensification in technologies in chemical engineering. So these are the domains are absorption domain, adsorption domain, stripping domain, distillation domain, heat transfer domain, fluidization, so and the liquid extraction, crystallization, reactions, centrifugal fields, dedusting or demisting, and bubbling domains. So these are some of the domains where the process intensification can be done individually. So these are, where you start that okay, I want to intensify the distillation process. So this is how you do. And the broad domains in the process intensification can be, so these are all the equipment specific domains, okay, and not equipment domain, but the process based domain, that okay, a particular absorption is a process and this has a domain. But these domains can be classified broadly in three different classes, where the process intensification happens in the domain of energy forms and transfer mechanisms. Or you can perform the process intensification in the synergistic integration of functions and steps. Or you can perform the process intensification via improving the time or the timing of the events and introducing dynamics. So these are the three broad domains. Now we can discuss individual examples of these domains. So I will just go briefly over them. So for the process intensification via energy, the focus on the process intensification via the energy forms and transfer mechanism. So these involve the focus is on the excitation of the targeted molecules, that okay, how well you can target the molecules and their excitations. And another focus is on the new operational windows, that okay, it is not just that okay, I operate on this particular window only. I can operate on different scales, that okay, I can operate my laser with 532 nanometers, and I can also operate my laser on 1000 nanometer range. So yeah, I can provide the energy through my laser with the 532 nanometer wavelength, or I can go with the 1000 nanometer wavelength. So yeah, these are my two operational windows, but it might happen that you might need a third operational window. So exploring or inclusion of new operational windows, and a selective local energy supply, that okay, how well you can supply energy locally on a particular area. So you might want to basically, for example, if you want to etch a particular surface, and if you want to etch on a particular area of that surface, and that is very very small, so how well you can etch that, so how well you can supply that energy locally to etch that surface. So that is the focus is, and the third focus is selective local energy supply. So the examples of this, of some of these idea or some of these focuses are microwave reactor, sonochemical reactor. Microwave reactor, we have just discussed that, okay, you can provide very uniform heating on a particular area and particular volume also. And supersonic gas liquid reactor, plasma photochemical reactor, spinning disk reactor that uses centrifugal fields, and magnetic field assisted reactor separator that uses again electromagnetic hydrodynamic effects to perform the reaction combined with separation. And supercritical separation fluid processes, ultrasound enhanced crystallization, acoustic field enhanced mass transfer, and hydrodynamic cavitation reactors. So now, so these were the energy, when you want to focus on the process intensification on the energy forms and transfer mechanism. Now if you want to perform process intensification with the focus on the synergistic integration of function and steps, then your focuses should be on the synergistic effects, and your focus should be on the overcoming the equilibrium limitations, and your focus should be also on how to make your equipment compact, and the last and very important focus, where you should be putting your focus, is how to increase my overall efficiency. So there some of the examples are membrane reactor and crystallization, membrane distillation absorption, membrane extraction, extractive distillation crystallization, distillation evaporation system, dividing wall column, reactive distillation, reactive absorption extraction, gas liquid solid trickle flow reactors, static mixer reactors. So these are some of the examples of the process intensification with the focus on the synergistic integration of function and steps. Now if you want to perform the process intensification with the focus on time, the timing of events, and introducing dynamics. So here the focus should be on the controlled energy input, that okay, if I want to have the laser, if I want to irradiate a particular process with a laser, and with the pulse duration of 10 nanosecond, 9 nanosecond, 4 nanosecond, so it's like the laser comes and just strikes the light strikes the surface, or the surface is exposed to the light for just 4 nanoseconds with the exposure time of just 4 nanoseconds. So you control that time, that small pulse duration of the laser. So yeah, so that is the controlled energy input, how well you can control that. And the second focus should be on increased energy efficiency, that okay, how efficiently you can give that energy. So once what is with the exposure time of 4 nanosecond, it should not be that okay, if your exposure time is very very small, your energy delivered should also be very very small. So the required energy should be delivered in that 4 nanosecond itself. So how efficiently you can deliver that energy is the focus. Another focus is minimized side reaction, that okay, even if you introduce the energy, can you reduce the can you minimize the duration where the side reactions happen? So that is another focus. So the examples of these three focuses are cyclic distillation, millisecond reactor, pulsing operation of multiphase reactors. So how you can pulse the multiphase reactors to perform certain mixing, and pulsed compression reactor, reverse flow reactors, oscillatory baffled reactors, oscillatory flow baffled reactors, pulsed combustion drying. So these are the focus for the these are the examples for the focus when the process intensification is performed with the focus on the time, the timing of events, and introducing dynamics. So I think all these slides would help you in performing in completing the assignments, and also to study for the course, and ultimately when you uh, would give the the last exam, the passing certificate exam for this course. So I think I would stop here today, and I will conclude the live session 1. So let us meet in the next week. So okay, so thank you.